So let's think about how we might be able to use a power series to represent a function. So let's think about this particular power series here. Let's suppose we've got the power series from n goes from 0 to infinity of just x to the n. A very simple power series. Now, if we expand this out a few terms, it would look like this, and it would just go on and on and on. Now, if you look at that, if you think about this power series, this is a geometric series because notice that there is a common ratio from term to term, and that common ratio is x. And so we would say that the sum of this series, this infinite series, is going to equal 1 over 1 minus x. This is something that we derived earlier, provided that that common ratio, the absolute value, is less than 1. So if that's true, we know that this is equal to this. So we've kind of rewritten this function. So we have this function, let's call it f of x, is 1 over 1 minus x. And that's exactly equal to 1 plus x squared, going on and on forever. So there. So so we've represented that function 1 over 1 minus x with a power series. Now let's play around with that a little bit. Let's think about this function. What if we take that same function and evaluate it at negative x? Let's see what that would look like. That would be 1 over 1 minus negative x, which is going to be 1 over 1 plus x. Now let's substitute in up here and see what we would have. We would have 1 plus a negative x plus a negative x squared plus a negative x cubed. And you can see we go on and on forever. But let's see what that would look like. Here's what we have. We have 1 over 1 plus x equals, let's see here, we got 1 minus x. Up here we've got negative x squared, so that would be a positive x squared. And you can see what's happening here. The odd powers change to negative. So we would have something that looks like this. Now, if we want to look at the summation, here's what the summation would look like. The summation would look like everything's the same as far as n equals 0 to infinity. However, now we've got an alternating series like this. Yeah, that's it. So we've got a couple of power series, a couple of functions that we can represent by power series. We have 1 over 1 minus x and 1 over 1 plus x. Now, I'm going to play around with this 1 over 1 plus x. Let me call that function g of x. Okay, so I've got g of x equals 1 over 1 plus x. And here's what I want to do with that one. I want to evaluate this function at x squared. So here I go. I've got g of x squared. Now that would, of course, be 1 over 1 plus x squared, like that. And let's see what that looks like when we plug it into the function here. Okay, so nothing changes with the 1. Now I've got minus x squared plus x to the 4th. See, I'm just squaring everything. So I have a 1, here's x squared, here's x to the 4th. This would be x to the 6th, like that. And then you can see it just goes on and on and on. And if we want to look at that with the summation, it would go like this. It would go n equals 0 to infinity, and it's going to be a negative 1 to the n, and then this would be x to the 2n, like that. And you can see if you've got this set up right, just start plugging in. If I plug in a 0 for n, notice I get 1. If I plug in a 1 for n, yeah, I get this term right here. If I plug in a 2, I get this one, 3, and so forth. So this is 1 plus x squared. Now, recall that that may look familiar to you, that 1 plus x squared, because remember the derivative of arctangent is 1 plus x squared. That's the derivative of arctangent. Well, if that's the derivative of arctangent, maybe we could find out what arctangent is. In other words, this is the power series expansion of the derivative of arctangent. Well, what if I want the antiderivative? What if I want to know the power series expansion of arctangent? Well, I ought to be able to just integrate term by term. So let's see how that would look. So let me just integrate this power series. So I've got n equals 0 to infinity, and I've got -1 to the n, x to the 2n, it's dx. So I'm going to integrate this thing. Well, let's see what that might look like. If we use the power series for integrals, it's going to be 1 over 2n plus 1 x to the 2n plus 1. And we've got the summation here. Okay, so it looks something like that. So this right here should be the power series expansion for arctangent, because here's the power series expansion for the derivative, and this would be the antiderivative. So I'm going back. I'm looking at the derivative here, so I'm saying, well, what did I differentiate to get that? What did I differentiate to get the derivative of arctangent? Well, arctangent. So this would be it. So let's see what this looks like term by term. Okay, so here's what we would have. We would have x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, and it would go on and on forever. Now, what we might want to do is check and make sure that those two things agree. Those two, the summation that we made and the power series. So let's see here. If I put a 0 in for n, let's see what I get. Well, I just get x. So I get that first term. Now, what if I put a 1 in for n? Well, I get negative. Okay, good, and -1. And then I get a 3 on the bottom. Good, check. If I put a 1 up here, I get a 3 here. Good. Yeah, it looks like it's going to work out. If I put a 2 in here, I get a 5 and 5. Yeah, yeah. So what we found is a power series expansion for arctan, and that's pretty amazing. This shows you the power of a power series. Now, of course, we are saying that the absolute value of x has got to be less than 1. So we're relying on this condition right here. But remember what we did was we started with this thing. We started with 1 over 1 minus x, and we got that from the geometric series, expanding the geometric series. And we said, well, that's just equal to x to the n. N goes from 0 to infinity. Okay, so this is where we started. And we found that we could find a lot of, we could use a power series to represent different functions. We did this one with arctan, but let's think about other functions that we might be able to find a power series expansion for. Now, for example, let's suppose that we have this function. Let's suppose we have 1 over 2 minus x. Now that's different than 1 minus x. So I wonder if we can find a power series expansion for that one. Well, what I need here is I need a 1. I need a 1 right where this 2 is. So what if I do this? What if I multiply the top and the bottom by 1/2 so that I get a 1/2 up top? When I multiply 2 by 1/2, I get a 1, and then I get x over 2 here. Okay, so all I did was multiply through by 1/2. Now, look, here's what it looks like. Instead of x, I've got x over 2. Now remember, so here was the original when I had x, but now I have x over 2. Now let me write this way. Let's put this as 1/2 times 1 over 1 minus x over 2. See? So I've got this 1/2, it's extra, but instead of x, I've got x over 2. Well, why don't I just do this? Why don't I write this as 1/2 and then do the summation, okay? And instead of x, I'm going to put x over 2. There. So 1 over 2 minus x is equal to this thing, provided, now we have to remember, the absolute value of x over 2 is less than 1. So that means that the absolute value of x is less than 2. Yeah, just multiplying by 2 there. So that's will give us our interval of convergence. Now, let's uh let's let's try another one. Let's suppose we've got 1 over, let's say we've got 3 plus x. Okay? Instead of 2 minus x, we've got a number. It could have been anything. 3 plus x. Now this is a plus here. Okay, so what we're thinking of here is we're thinking about this function here, 1 plus x. And remember, we said this one was 1 minus x plus x squared minus x cubed plus, and it went all the way out here, and it was an alternating series. So we're thinking about this series here. Okay, so there's our series. So let's do this. I still need a 1 here. I need a 1 here. So I'm going to multiply the top and the bottom by 1/3, and I get 1 plus x over 3. So it looks like this is going to be 1/3. See, I've got the 1/3 here times 1 over 1 plus x over 3. And now just plug into our power series. So here's what we've got. We've got 1/3, and this is the n goes from 0 to infinity of -1 to the n, x over 3. And that is provided that x over 3 in absolute value is less than 1, or the absolute value of x is less than 3. So, there you see. Now, here's the thing about these expansions, these power series expansions. These are said to be expansions about 0. So we're expanding these around x equals 0. Now, what we're going to look at next is, well, what happens when you do expansions around something that's not 0? So that's our next